If the total work done on a body is positive, the work speeds up. If it's negative, the body slows down. And if 0, the body experiences 0 change in speed. This is kind of what we finished off looking at last video. So in this way, though, the total work is related to a body's change in speed. So if you look at this, and you consider a box that has some mass and starting at x1, velocity, it has velocity 1. It might be stopped, it might not, but it has velocity 1. And if it has some force that's being applied to the right through this whole displacement s, then by the time it gets here, v2 is going to be greater because you're pushing it in this direction. So even if it already had some speed, v2 is going to be greater than v1. If the net force was the other direction, then the net force would be slowing it down, and so you'd be getting v2 less than v1, right? And if the net force were some completely orthogonal direction to the direction of motion, then v1 would equal v2. This is what we looked at last time, but I'm just exaggerating or explicitly stating that it's relating to the velocity, because what we're going to do is we're going to start with work. We're going to use one of our equations that we're already familiar with, and we're going to arrive at something called energy, which is related to the speed, or kinetic energy at least, is related to the speed. So, I'll use white. Hopefully you don't think white is too boring. I'll use white. So, we're going to start off using a constant and acceleration equation, and it's going to be this one, and you can probably go back and make sure that I've gotten this right. And remember where we came up with this. All right. But we're going to do some substitutions. So we're going to call v naught x v1, right? Because that's basically what it is anyway. So v naught x, we're going to call v1. Vx, we're going to call v2. And this whole x minus x naught quantity, we're going to call s, because that's displacement, right? x2 minus x1. So if we make those substitutions, then what we're left with is v2 squared is equal to v1 squared plus 2a x s. Just a little bit simpler way to write it. Now we're going to solve for the acceleration. So a, acceleration in the x direction, is equal to v2 squared minus v1 squared over 2s. All right. So if we multiply both sides of this equation by mass right now, we can get force on the left side via Newton's second law, right? So force is equal to F equals ma, right? We'll keep that x. max, acceleration in the x direction. And so then all we've done is multiplied by mass on this side as well. So we have mass times v2 squared minus v1 squared over 2s. This is just all in the process to get somewhere, so you don't have to remember this whole process. This is just to show where things come from. I think it's useful. Then if we bring displacement over onto the left side, we have work on the left side, right? So we bring displacement over. So F times S, we've just learned, is equal to work. So I'll say work is equal to Fs. And so all that we've done here is we've gotten 1/2 mv squared, 2 squared minus 1/2 mv1 squared. I just kind of distributed it out, right? And so look at that for a little bit and see what we've arrived at. What we have is this quantity 1/2 mv squared, right, and the difference in velocities before and after. But what we've arrived at is the net work is equal to the difference in something. What is that something? What is that 1/2 mv squared thing in there? Well, that quantity 1/2 mv squared is what we call kinetic energy, K. So kinetic energy. And it's abbreviated with a capital K. So K is equal to 1/2 mv squared. And this is worth jotting down. And so this is kinetic energy, one of the things we wanted to arrive at. But more specifically, if you look up here, you have kinetic energy in the after scenario, and then kinetic energy in the before scenario. So where it starts and where it ends. Kinetic energy of where it was before the net force started acting on it, kinetic energy after the net force has acted on it through that displacement. And so what that is called, this relation that we arrived at, is the work energy theorem. So the work total, the total work, is equal to K2 minus K1, or delta K. This is the work energy theorem, this concept here, that the work that's done is equal to the difference in kinetic energy. Right? So this is the work energy theorem. It's going to allow you to solve a lot of complex problems very simply, so you're going to love this thing. This concept of energy allows you in general to do that, of solving more complex things that our tools that we've learned thus far didn't allow us to be able to solve. So, before we go much further, we've just introduced some concept of work, which I just said is defined a certain way. A force applied in the direction of motion, right? So force times displacement. And then we came across this kinetic energy thing, and I said it's equal to 1/2 mv squared. But what even is kinetic energy exactly? We have a colloquial understanding of what energy is. We use that in everyday speak. How close is it to the physics definition? What is kinetic energy versus other energy exactly? Well, so other than just 1/2 mv squared, kinetic energy is often called the energy of motion, because a body that is moving possesses energy in the form of its motion. So looking at the equation for kinetic energy, 1/2 mv squared, a body's kinetic energy scales linearly with its mass, right, and quadratically with its speed. So the faster something's going, the more motion it's experiencing, its kinetic energy goes up dramatically. It goes up by the square of velocity. So mass can't be 0, it certainly can't be negative, and speed can't be 0. Well, speed can be 0, but it can't be negative. Negative velocity just means a certain speed in a different direction, right? So velocity can be negative, but speed can't be negative. You're just going some positive speed in some direction, but speed does not have anything to do with direction. So speed is always positive or 0. So what that means is that kinetic energy cannot be negative. It can only be 0 when the body is at rest, or positive when it's in motion. And so you can kind of see that kinetic energy quantifies a body's motion. If its body's motion is 0, then kinetic energy is 0. If a body's motion is greater than 0, greater than nothing, if it's moving, then kinetic energy is going to scale with it. So if we apply a constant force to a particle that starts at rest, it accelerates, right, via F equals ma. The work energy theorem tells us that the kinetic energy of the particle is equal to the total work that was done to accelerate it from rest to its present speed. So that's one maybe working definition for you to think about what kinetic energy actually physically means. Kinetic energy is the amount of work that got it moving. So if we come back here, whatever kinetic energy this thing possesses with its mass and its speed, it's equal to the amount of work that it took to get it to that speed. So if V1 is 0, then the kinetic energy here is the amount of work that it took to get this mass, this amount of mass, to this speed from a stop. Okay. So that kind of is consistent with our working English definition of energy. It's just the amount of energy that it takes to get something going. So that kind of translates all right. Here's an alternative definition, or an alternative concept to try to let sink in. So if we apply a constant force to the moving particle or box that we got going in the reverse direction so that it slows down to a stop, the work energy theorem reminds us of Newton's third law and tells us that the kinetic energy of the particle is equal to the total work that particle can do in the process of being brought to rest. So as something is slowing down, so this box that we have, it has some velocity now. And as we apply some force to it this way to slow it down, if that's our hand, right? I'm not good at drawing hands, but if that's our hand, the box, if our hand is pushing this force, then the box is going to be pushing back on our hand just as much as it slows down, right? So we're talking about two different bodies. Newton's third law, that's that conundrum we talked about before. So the hand is applying a force to the box is applying a force back to our hand. So think about like catching a baseball barehanded, if you've ever done that. Somebody throws a baseball at you, it's a pretty hard ball, and you catch it barehanded. If you catch it and you don't move your hand back at all, it kind of hurts if you try to just catch it with your hand being completely stationary. It's much easier to catch that ball if you move your hand backwards as you're catching it. And so the reason for this is because the amount of work, so work is equal to Fs, right? So this is the displacement. So if you move your hand back as you're catching, I guess this is now a baseball, the squarest baseball that ever existed. Eh? Almost looks like a football. If you move your hand back through this displacement S, then you're maximizing this S value, and so therefore you're minimizing the force that's being applied to you because the work is the same. So if you're taking this baseball and you're bringing it to a stop in this distance so that it has no velocity, or you're bringing it to a stop period, even if you kept your hand here, the work done is the same because the work is equal to the amount of kinetic energy that the ball has and to bring it to a stop from its current motion. So if you exaggerate the displacement that you're bringing it to a stop over, then the force can go down. Here, let me write this differently. So if this goes up, this goes down, right? Because this stays constant. Or if S goes down, F goes up. So what if the displacement here was 0? So if the displacement there was 0, would force have to be infinite, something infinite, in order for the work to remain some finite positive number? So it kind of makes you think, when you're catching something, you're never going to be able to catch it at a dead stop. Even when things hit a brick wall, the wall still gives a little bit. You might not notice it, but the wall still gives a little bit. And the ball gives more. So there's always some sort of displacement. Yeah, so hopefully that gives you some sort of an intuitive definition for what kinetic energy is, what work is. Kinetic energy, if you just think of kinetic energy as the energy of motion, that gets you pretty far down the road. And if you think about trying to feel physically what kinetic energy might translate to in terms of physically feeling it, then you can think of catching a ball and how much work it's doing on your hand to bring that ball to a stop, or pushing on something and how much work it takes to get it going. So energy and work have the same units. So the units of work, how should I write this? Units of work was the joule, and that's the same as the units of energy. Units is also the joule. This is Newton meters, right? All right. So that is all I have for this video. No, we're going to do an example. Okay, there we go. All right, let's do one example and then we move on to the next one. So here's an example. I chose this example specifically to show you how this might help you solve things that would otherwise be kind of complicated, but it becomes pretty easy when you have this concept of work and kinetic energy. So, stopping distance, just like we were speaking about with the baseball, but I don't think it's talking about a baseball here. Alright, you see that okay? Alright, a car is traveling on a level road with speed v0 at the instant when the brakes lock, so that the tires slide rather than roll. So that's important for friction, right? It would be a different kind of friction if we were having rolling friction versus just sliding friction. A, use the work energy theorem to calculate the minimum stopping distance of the car in terms of v0, g, and the coefficient of kinetic friction, mu sub k, between the tires and the road. And then part B asks us to analyze some things. So what is our situation here? What are we trying to find here? Minimum stopping distance, right? So the minimum stopping distance would be the displacement, s, right? Some distance. So s equals something. That's what we're trying to find, at least for A. And let's draw a simple sketch of what's going on. So we got a car going on a road. This is the road. I always like to do these to show it's solid ground. This is going to be our car here. It has some mass, I guess. Yeah. And it has some initial speed, v0, which is not 0 because it's traveling and it's ending up at a stop. I'm going to write mu sub k here to remind us that we are considering the coefficient of friction. There is friction against the road. And then over here somewhere we have v, a final velocity of 0. And what we want is the displacement. This is S1, and this is S2. That's kind of what we want. And so S we'll say is equal to delta S here. I guess I should use X instead. X1, X2, and displacement is equal to delta X. Alright, you get the point. So now the next point, the next thing to do, I'll switch back to colors because they're pretty, is to do a free body diagram. So we have some gravitational force, some normal force, we have coefficient of the friction force, kinetic friction. So here's gravitational force. I'm going to do, it gives us, what way does it give us things? It gives us, it says that he wants it in terms of G, so I'll write mg. This is the normal force. Normal force is going to be equal to mg as well because it's not going up or down. So I'll just write mg. It's obviously in a different direction, but that's the magnitude that it's equal to, just to get us going. And then here, that's okay, that's kind of written out very clearly. F, so K, what that really is equal to is the normal force times mu sub K, if you remember what our friction stuff was. And the normal force we know is mg, so I'm just going to get this going right on this diagram. So mg mu sub K. Alright, so now we got some stuff already figured out. You don't have to go that far with your free body diagram. Sometimes it's useful since you already know where the problem is heading. Alright, so instead of finding the sum of the forces in the x and the sum of the forces in y and going with our Newton powers, our Newton's tools, we're going to go with kinetic energy and work. And it gives us a hint. It says use the work energy theorem. So it kind of leads you into, we want you to use this. It would probably be easier, so we're going to take that hint. So what's K1? Right, so the work energy theorem, let me write it up here one more time. The total work is equal to K2 minus K1. That's the work energy theorem. So that's what we are trying to use here. So what we must find is K2 and K1. K2 is K standing for kinetic energy, right? So K2 here. The car is still going to have mass when it comes to a stop. And we're still going to have this 1/2 factor. So 1/2 mv squared. And the v would be when it comes to a stop. So v is 0. Alright, so K2 is 0 because v is 0, right? So that's 0. So let's come to a stop. But K1 K1 is 1/2 mv naught squared. I'm going to do this. Goes to 0. I don't know if you can tell. Goes to 0. But K1 is 1/2 mv naught squared. And it doesn't give us any numbers. We're just doing this in symbols. What is it that we wanted? We wanted S, right? Well, let's keep going with the work energy theorem. So the total work that's happening to bring this car to a stop is equal to K2 minus K1, but K2 is 0, right? So the total work is equal to 1/2 mv naught squared. Right? I guess that'd be negative. And that's equal to, work is also equal to Fs, right? And so F, in this case, is the sum of the forces in the x direction. So, or the sum of the forces in the direction of motion. So if this is x here, right? Then the motion is in the positive x direction. And so that means that this would be the x direction. And that means that this, which we've gone all the way to figure out, is mg mu sub k. That would be in the negative x direction. And that is the component of force that matters, because that's the component of force that's in the direction of motion, which is what work is all about. So that would be, let me go back to the right color here. That would be mg mu sub k times s, right? So excellent. We have our s here, which is what we're trying to solve for. We have stuff on the left and stuff on the right. This is in the negative x direction, so it's like that. And so we can just simply solve for s and make sure that we've done it in all the right things that they wanted us to solve it in terms of. So I'm going to rewrite this and this here, right? So that's what we're really after. So we have negative 1/2 mv naught squared is equal to negative mg mu sub k s. Well, there's a negative on both sides, so that goes away. There's also an m on both sides, so that goes away. And we're solving for s. So s is equal to 1/2 v naught squared over g mu sub k. Is that everything they wanted us to solve it in terms of? Let's go back and make sure. So it says solve it in terms of v naught, g, and mu sub k. I think we did it. V naught g mu sub k. There we go. So if you like, you can go back and try to solve that using Newton's laws. It would be much, much more complicated. Or you can just take your unwillingness to go back and solve it with Newton's laws as proof that this is the easier way. All right, so then part B tells us to analyze this, this stuff. I'm just going to bring out a new copy of this. All right, so B said, by what factor would the minimum stopping distance change if the coefficient of kinetic friction were doubled? So if this were doubled, how would it change? Well, if that were doubled, then s would halve, because you'd just be adding another 2 on the denominator. So s would be halved. If so for friction, if you're thinking about it in real terms, if the friction between the tires and the road had doubled, then the stopping distance is cut in half. If the initial speed were doubled, if the initial speed were twice as much, the car is going twice as fast, well, speed is to the square here. So if speed were doubled, then the stopping distance would quadruple. It would be 4 times. Or if both the coefficient of kinetic friction and the initial speed were doubled. So if you get twice the friction, but you have twice the speed, well, this is doubled, so it's times 4, but this is doubled, so it's halved, so you get a doubling of the distance overall. So it just shows that the speed is much more, plays a much bigger role than the friction between the tires and the road. So when you speed up, when you're going real fast on the freeway, you got to take into account stopping distance. Even if you got really wide, sticky tires, your speed plays much, much more of a role. All right, that's it for this video.